Hi everyone. In this video, I want to continue with my review of some topics from statics, and specifically I want to talk about forces and moments and what we need to consider or at least remember from those when we get to dynamics. So again, this is a review topic, and I want to talk about static equilibrium and how that comes into play with forces and moments. So, as you may recall, static equilibrium is something that we take into account. Try my best to actually spell things correctly. Something that we take into account when we have things that aren't moving. And that could be a particle, like a baseball or a ping pong ball. It could be a rigid body, so something larger that has a little bit more geometry to it. But the net effect is that we can have an object and we can have things like forces applied to it. And those forces can be applied anywhere. Let's just pretend we have a 40 Newton force here and a 10 Newton force here. And static equilibrium dictates that if this object is not moving, or more accurately not accelerating, then we have a state of condition that looks like this, that the sum of forces in the x is 0, the sum of forces in the y is 0, and the summation of moments around some point, any point that we define, should be 0. And this gives us that condition of static equilibrium. And some things that we should note here are that we have two components of force, and that again is because force is a vector quantity. So if we want to do this mathematically, we would often split it up into its Cartesian components. Note that we only have two because I've simplified this problem as a planar problem, meaning I'm only working with 3 degrees of freedom, which is up and down motion, left to right motion, and rotation. And if I were to expand this, so let's just label this 2D. If I were to expand this to 3 dimensions, then I would need to retain my summation of forces in the x and summation of forces in the y. And now I would add to it a summation of forces in that third direction, often called z. And my summation of moments now gets a little messier as well, in that I can sum around the x-axis, sum the moments around the y-axis, and sum the moments around the z-axis. So put a big box around all those. But basically this is to say in 3 dimensions we have 6 degrees of freedom, and our object could move in any one of those 6 degrees of freedom. So we have translation up and down, left to right, in and out. We have rotation around 1 axis, 2 axes, 3 axes, all of which would need to be constrained to have their forces and moments be equal to 0. All of those, again, are vector quantities, and we've broken them into Cartesian components based on a standard Cartesian coordinate system. Now, forces, hopefully people would have a pretty good sense of or remembering what forces are from a course in statics. We would also, as I've mentioned, have moments. Moments are sometimes defined simply as force times distance. So if I have, let's just take an example, a rigid structure. This is a cantilevered beam, and I apply a force out here, which is at some distance d from where this is fixed into the wall. This force applied at a distance creates a moment and a reaction moment, which is equal to that force times that distance. More generically, I might write my moment as a vector quantity, which it is, a rotation vector in this case, equal to a position vector crossed with a force vector. And this is more generic in that it doesn't presume orientation of my force and my distance. When I took this, or made this simplification of moment equals force times distance, that is only true if this distance d is perpendicular to the direction of action of my force vector F. So this vectorized version of the equation is a little bit more generic. I can write this out or expand this out in a two-dimensional Cartesian coordinate system by writing fx times dy plus fy times dx. Now what I'm doing here is saying that the x component of my force gets multiplied by the y component of my position or distance, so that's the y distance, and that gets added to the y component of my force multiplied by the x distance. So I might break that force vector down into those two components and then break the direction, the measurements down into those two components and make that simplification. So this is a little bit more robust in that it isn't dependent on the direction of force. So if, for example, just get a different color here for differentiation, if, for example, my force vector looked more like this at an angle, then I would need to know the perpendicular distance, which I could still do f times d if I knew this perpendicular distance, the blue letter d there, or I would break this force into x and y components, and then I would know the distances between those things in the x and y directions as well. So that allows me to break it down and still calculate a resulting moment, even if my geometry isn't nice and perpendicular in all circumstances. These forces and these moments are important because they lead to where we're going in dynamics. And that is, when we have forces and moments present, if our object that those are applied to isn't constrained, prevented from moving, then it starts moving, right? And we get accelerations that we have to deal with and start thinking about from a dynamic sense in terms of how this object or this thing is going to be moving. And that's where we'll be going next in this course. All right, thank you.